Uh, okay, so first of all, thanks very much, Francesco, for inviting me to give this seminar. It's a great pleasure. So my name is Emiliano Renzi. I'm a professor of industrial mathematics at Northumbria University, which is in Newcastle in the UK. So it's in the northeast of the UK, close to Scotland. And today, actually, I'm going to present you something broad about several aspects that I've been dealing with in my research, starting from my postdoctoral years in Ireland all the way to my position as professor now at Northumbria. And the broad sort of umbrella under which I work is that of mathematical fluid dynamics or mechanics for sustainable development, and in particular applied also to extreme waves. I will start with less extreme waves at the beginning and then move to more and more extreme waves towards the end. So I just wanted to mention that my research has been supported by several institutions, the Science Foundation Ireland during the time I was in Ireland, then AXA Research Fund. So I've got this fellowship from AXA, is an insurance company. And then here in the UK, the Engineering and Physical Sciences Research Council and the Royal Society. So let me start with a broad overview of what I do. So normally what I do is analytical and computational models for with application to the sustainable development of coastal cities. So in particular, I work on two main applications. One is the design and optimization of offshore renewable energy systems. So here you can see an example of offshore wind turbines. And on the other end of the spectrum, I mean, of my activity, it's still wave energy, but it's a very different type of wave energy in the sense that this energy is very destructive. And so what we do in our group is also to develop models to understand coastal hazards and also to understand how we can mitigate them. And today I will show you several examples from both these areas of what I do. So let me start with wave power. Here you can see the world wave power resource map. So here, essentially, that's the map of the world. And you can see in different colors how energetic the oceans are in different parts of the world. So the blue color is not really energetic, and all the way down to green, yellow, and red, which are really energetic. So starting from the US, for example, well, the East Coast, I'm afraid, is not that energetic, though, I mean, the Carolinas are pretty okay. They have quite a good amount of wave energy. Georgia, not much, I'm sorry. But on the West Coast is very much really energetic. So starting from California all the way up to Oregon, Washington, and Canada, and also Alaska, you can see that is one of the most energetic areas in the world. So there is also in the US a lot of interest in how we can actually exploit all this massive energy that's in the ocean to generate electricity, because at the moment that's totally unexploited. In other areas of the world, there is quite a lot of potential in South Africa, for example, South America, Australia. They have a lot of energy along the south coast. And now moving to Europe, if we zoom, that's the UK where I am right here where the mouse, my pointer is. So that's Newcastle. And you can see that there is quite a good amount of energy on the East Coast. But in some sense, you know, the UK is similar to the US. The East Coast is not that energetic, but the West Coast, especially this area, Scotland, and then moving also to Northern Ireland here and the Republic of Ireland is very energetic. So it's one of the most, again, one of the most energetic areas of the world. And so that's why there is a lot of interest also in the UK on the development of this type of technologies. So what are these technologies? This is just an example. There are so many, but in my career, I've been working on this particular type because what Francesco was saying is I've been already working on flaps, essentially, to protect Venice from the coast, and hydrodynamically, they are very similar. These devices are very similar to the flaps that I've installed in Venice, but these are not to protect the coast, but to extract energy from the waves. So you can see several designs which have been patented by several companies. These are European companies mostly. There is an American company in Boston that have developed, Massachusetts, that have developed similar devices, and they are designing this type of devices. And these are called oscillating wave surge converters. So these are flaps, they move back and forth under the action of the waves. And here, normally at the hinge, it depends really on the design, but normally here at the hinge, there is a generator. And so these move back and forth. The generator is like a dynamo, really, the one that you might have, for example, on your bike. And so because of this motion, they transform wave motion into electricity. Now, what we do in terms of our group is that we develop mathematical and engineering models to design and optimize these devices. These devices, there is no doubt that they work, but of course, to make them competitive with respect to other sources of energy, we really need to optimize them. So we really need to decrease their costs and make them more efficient. And before starting to show you the details of what we do, I just wanted to recap some, very generic wave theory, because probably I'm not sure whether all of you know something about waves, but this is, a very quick recap. So we have, of course, imagine like a sine wave. We have crests and troughs, and the distance between a crest and a trough is called the wave height. Half of the wave height is the wave amplitude, so it's the amount of water that's above the undisturbed sea level. And the distance between two crests is called wavelength. And I will use these concepts a lot, so I thought it would be good to start with this. Now, this is a plot in space. If we plot a wave in time, we have a very similar concept to the wavelength, but it's the period. So if we plot a wave with respect to time, so time is on the x-axis here, and the displacement is on the vertical axis, we can see that the distance between two crests or two same points, similar points on the wave curve is called a period. For example, here we have 1, 2, 3 periods, and the inverse of the period is called the frequency. So if we have long periods, we have very long waves. Large periods, we have long waves. Small periods, we have shorter waves, and that's the inverse with the frequency. So the higher the frequency, the more these waves oscillate. So these are very, very simple concepts that I will keep using in my presentation. Right, so let's start then with the mathematical models. I promise I'll be very, sorry?
Gentle. No, it's fine, don't worry about it.
Can you hear me?
Yes, we can, yes.
Okay, great. So I will not put too much mathematics into my slides. So don't be scared. I will explain you the maths in a moment. So we start with linear models. These models are very useful when the oscillation of the flap, so here this is the mathematical idealization of the device. So we have the flap, the hinge, and the flap is normally hinged upon a foundation, and the waves are here on top of the surface. Now, when the flap oscillates by about 10 degrees, so not much, we can use these linearized models. So these are not really extreme waves. Later on, I will show you what happens in extreme waves. But for the moment, let's start with, normal waves, like 1 meter amplitude, okay? And so these are the equations that we use. For those of you who are familiar with this is a system of partial differential equations with boundary conditions. So this is the equation which is called the Laplace equation, which we normally solve for this type of problems. And these are boundary conditions that are applied on the surface and on the flap, on the foundation, and also on all the physical boundaries, also on the seabed. Now, without going into much detail, there are several techniques that we use to solve these equations. In particular, for this particular system, we used what are called hypersingular integral equations. But really, I want to show you the results of these models. So these models then allow us to calculate the velocity field in the fluid and then the pressure, and from the pressure we can get the power output. So these are really powerful models that allow us to calculate the performance of the device and then to optimize the device. So in this case, it would be, the optimization would be change the geometry of the device so that it produces more energy. First of all, of course, we always need in engineering and mathematics to validate our models, and the way we do it is with experiments normally. So here you can see, and now I start to use this concept that I've introduced before. On the x-axis, we have the frequency of the wave, and on the vertical axis, it's the wave torque, which acts on the device. And the blue line is the model results, and the diamonds are the experiments. The experiments were performed by some collaborators of ours at Queen's University in Belfast, in Northern Ireland. And you can see here they have a really nice wave basin. This is the experimental device that they've used. And we've compared the results, the model results with the experimental results, and you can see that there is really, really good agreement between the experimental data and our model. And what is interesting is that if you noticed in my previous slide, here we are modeling a flat flap. Later on, we show you what happens when the flap is not flat. Whereas their model is made by cylinders, but as long as the waves are small, so the oscillation is more or less, well, less than 10 degrees, the shape of the device doesn't really influence the results. That is a nonlinear effect which comes into play when the oscillation is stronger, okay? And of course, we also compare with other numerical models, and again, we validated, fully validated our results. Now, once we are sure that our model works, then we can extend it to optimize the device. So here, for example, there is an example of optimization where we calculated different parameters, the added inertia, radiation damping, exciting torque, but the most important is this one, the capture factor, which is really a measure of the efficiency of the device. So we want to push it as close to 1 as possible, really. This is for calculated for different widths of the device. So the first one is 12 meters, then we increase to 18 meters and then to 26 meters. And we can see that there is a different behavior. So depending on the period. So here on the x-axis, we have the period, vertical axis is the efficiency. So this means that we can engineer, we can design the width of the device to peak where we want it to peak in terms of the period. So if the peak period of the incident waves is around 5 seconds, then the best device, the most promising one, is 12 meters. But if it's larger, then it can be 18 or 26 meters. These are some examples on how we can use this model then to really design some elements of the device. So in this case, for example, the width, of course, we can apply this to many other engineering aspects of the device. Now, we move then to something more complex, because a single device is definitely not enough. We need more devices, so what we call arrays, where we have different several devices. Normally, all of the devices are of the same type, but arranged into several configurations. So in this case, we have more than one device, and they make an array. Now here, the mathematics is more complicated. These equations are the same, but of course, since we have now the physical presence of more than one device, we need to apply mathematically boundary conditions on each of these devices, and then that takes longer, but it's something that we were able to solve. And now again, I want to show you the results. So in terms of the mathematical aspects, we still have a Laplace equation to solve boundary conditions, but each boundary condition now is for each of these devices. So the individual device is called device M. So M is 1, 2, 3, 4, 5. We model up to 40 devices in this case, where big M here is the total number of devices that we modeled. So for example, with this, we can start with fun, because of course we can not only now design the single with the single parameters of the single device, but also we can design how they are arranged into this array. So these are this is our top views of the system. We can have devices arranged, for example, in an inline configuration. Each of these yellow lines is representing a device as you see them from top. Imagine you are a bird flying over this ocean, and you see these devices from the top. Then we can also stagger them like this, or even more, a more staggered configuration, or we can have an inverted upside down V configuration or a V configuration, and many others. But these are, the ones that are mostly used, and so we wanted to see how they perform. This plot is again another plot that tells us how they perform. So once we solve the system, then we can plot the behavior of the devices with respect of each of these configurations with respect to the period. So again, here we have the period of the waves. Now on the vertical axis, again, we have the efficiency. Now, this is not the thermodynamical efficiency. So as you can see, it can get more than one, because in this case, when it's more than one, it means that the devices are effectively collaborating to extract more energy as they would if they were isolated, okay? So in this case, this, for example, for this black curve, it's the 13 flaps in line. It means that in this region, they are working better than if they were working in isolation one by one. But there are other regions where the interference is called destructive, so they don't go well, you know, they don't agree well on what to do, and their interference is destructive, which is, of course, something that we want to avoid. But you can see already in these plots that depending on the configuration, we have more or less efficiency. And so again, depending on the type of period that we know from metocean analysis, so people that work in metocean normally give us the prevalent sea state conditions, so the period, the amplitude of the waves. So if we know the period, then we can design these devices and the configuration of these devices in a way that we can extract more energy, so as to optimize the system. Then let's move to something even more interesting than this, weakly nonlinear. So we start to consider now oscillations of the flap that are in more energetic sea states, so more than 10 degrees, between say 10 and 20 degrees, and that's called the weakly nonlinear regime. And now in this case, we showed in our work that the shape of the device becomes important. In the linear system, in the linear case, the shape of the device is not really important. Here it is important. So we also studied, not only we extended our analysis to nonlinear cases where the devices move by a larger degree, but also when the shape of the device is not flat. So here you can see that we have some curvature for the device. Well, then this means introducing two more parameters. This epsilon here is a nonlinearity parameter. This mu is a shape parameter. So as you can imagine, the maths becomes more difficult. In particular, the boundary conditions are much more difficult than before. But my postdoc was really brilliant, was able to find a way to solve this mathematically, so we have the solutions. And I can show you some interesting results. Again, I will skip all the maths and show you the more sort of engineering aspects, of the aspects of engineering interest for the device. And this in particular is one device with normal incidence, so the waves are coming just in front of the device. And here we have different geometries. So this flat is the flat configuration, the vertical wall essentially, where the flap is a vertical wall, and delta 1, delta 2, and so on are different configurations. In particular, as you can see and this is the frequency. So for small frequency, relatively long waves, it doesn't matter whether we change the device shape or not, we still have the same, all the curves superimposed. But for larger frequencies, the curves are different. And in particular, if you follow this curve is the one with the flat device, and these other curves are the ones with different geometries. In particular, we found that if we use these two types of geometries, so the flap is not flat any longer, but is concave, as you can see here. So we can give them some curvature. Here is on the vertical, and here is also on the horizontal and the vertical. So if we change the shape of the device, then we can extract even more energy. So this is something that we can use to optimize the device even more. And this is really because of a focusing effect, because the shape of the device focuses energy close to the system, and then we can extract it. I will show you cases later on, applied to oceanography mostly, where we have similar focusing effects, which are instead very detrimental for other reasons, in particular for navigation. But in this case, we like this effect. So this focusing effect that we can use to optimize the device. So just to recap this first part, we've seen that in the linear regime, we could develop several models. The behavior of the flap is not really affected by shape effects, but we can optimize the device by using these linearized models. In the weakly nonlinear regime, so in more energetic waves, then we can have, by engineering the design of the device, so that it has essentially a concave shape, we can have a 20% increase in efficiency, which is really good. Well, these are the main results that I've shown you today about this particular configuration. Now let's move to something really energetic. So here there are extreme waves. And of course, when things become more extreme in the water, it's almost impossible to solve them. Well, I show you it's not always the case, but it's really difficult to solve them mathematically. And so we start with other models. In this case, we did experiments. So here you can see photos from this experiment. This is the flap. It's hinged on the seabed of a wave tank, and this is the wave incoming. And this is called slamming. So when we have really large waves, imagine that in real life the device height is 13 meters, so it's pretty high, like a 4-story building more or less. So it's pretty tall, and this wave is higher than that because it's going on top of it. So this is really an extreme waves. And what happens is that first of all the flap is submerged, and then it starts to re-emerge, as you can see here. Then it moves vertical. At some point it is vertical, and here this is a really important phenomenon. You can see that there are some bubbles, so some air is being trapped here, and then there is the slamming phase. So the device hits the water and creates a jet here. So this jet is ejected, and that's the end of what is called the slamming phase. I should say that these experiments were done by, at the time, my advisor, now my collaborator, Professor Frederick Diaz in Marseille, where they have a fantastic lab. And so what can we do about this? Well, first of all, this phenomenon is really difficult to understand because we did several experiments, 27 repetitions of the same experiments that you can see here. So here, you can neglect this plot here and concentrate on the one on the right. So on the x-axis, we have time, and on the vertical axis, we have the pressure at the input measured on a sensor. So we put a sensor on the device and we measure the pressure. And you can see that we have completely different values. So each of these curves is one run of the experiments, and we did not change the conditions of the experiments. It was exactly the same experiment, but gave 27 different results. And this is because this behavior is very stochastic. It's very difficult to reproduce because there is a strong space-time localization. This input is very much localized in space and in time. The surface deformation is very nonlinear, so it can change, even if you repeat the same experiment, sometimes you don't have exactly the same surface deformation given by the wave, and then you have completely different results. And also the way air is entrapped, and that also, of course, depends on the circulation of the air inside the building where we did the experiments. Depending on how much air is entrapped, you have completely different results. This means that this is really difficult to model. So we started with some computational fluid dynamics. CFD stands for essentially computer models of this system. So we gave the system, we used essentially off-the-shelf software. We gave it the configuration, generated the waves, and calculated the pressure. And again, the blue lines here, this is the same plot as before. For the blue lines, they are the same. So they are the experiments. And the red line is the CFD simulations. You can neglect the green lines are some averages on the experiments, but this is more, or data extrapolated from the experiments, but we only compare the blue line and the red lines. As you can see, the computational model is completely off. And the results are off by a factor 10, which is really not acceptable in engineering. There's no way we can use this model to design the device to withstand these waves. So what we did is something different. We used a really, really clever approach, which was devised by Cooker and Peregrine. Peregrine is one of the greatest minds really in the world of wave modeling. And they thought, well, instead of calculating the pressure, which is really difficult, they did this many years before. They developed this idea many years before, but they didn't apply it to this system. So we are the first to apply to this system. So the idea is, instead of focusing on the pressure, which is really hard to calculate and to model, why don't we focus on the integral of the pressure with respect to time. So we consider the amount, essentially an interval of time during which we have this extreme event of slamming, and then we integrate the pressure over this time. And this is called, what we get is called the pressure impulse. And this is much better behaved than the normal pressure. And what we then realized several years later after Cooker and Peregrine is that we can actually use this system on our wave energy converter. And it was surprising to see that we can even solve it analytically. And in fact, we can even solve it by hand if we don't concentrate on the pressure, but on the pressure impulse, because the pressure impulse satisfies very similar equations to those I showed you before. So again, we have a Laplace equation with boundary conditions. And in fact, we can even calculate the effect of the air pocket. We can insert wave pocket, which is modeled by this function f here. And depending on the shape of the air pocket and how much air is entrapped, we can have different results. So using this pressure impulse was really phenomenal in that sense, because it really allowed us to solve this problem and get much better results than the computational simulations. So we solved the problem, and then once we solve the problem, we can plot the behavior of the pressure impulse. So here on the x-axis, we have the pressure impulse. So, and on the vertical axis, we have the distance from the seabed. So the seabed is here. And we can see also what is the effect of the air. And the more air is entrapped, the higher the pressure impulse on the flap is. So in some sense, air entrapment is not good, because that increases the violence of this impact on the flap. And once we have the pressure impulse, then we can do some nice calculations to get the pressure. So for the pressure impulse, we can go back to the pressure and calculate. We cannot have, you know, a nice diagram of all the pressures at all points. This method is not doesn't allow us to do that. But what we can do is calculate the maximum pressure on the device, which is really the engineering parameter which is most important for us, because we want to make sure that that pressure is not high enough to destroy the device. And if we now compare the maximum pressure at the sensor, so we calculated our results at the same position where we put the sensor into the wave tank, we can see that our results are much, much closer to the experimental results, and the range of change of the pressure, the maximum pressure, is really within the same range that we have in the experiments. So this model works much better than the computational model, because it's based on a different concept of pressure impulse. And so let me give you a recap on this. So I showed you an example where we have now very, very energetic waves, extreme waves acting on this device. I showed you that we can obtain a reliable estimate of the maximum pressure with really no computational cost, and it works much better than computational fluid dynamics models. And of course, we can use this to optimize the design process. I'm not saying that we shouldn't use computational fluid dynamic models. In fact, what this the idea behind this project is to be able to use this as a preliminary estimate, so that we know the cases that produce the highest pressure, and then we can refine the result by using computational fluid dynamic models, which are really essential. So it's not that we are going to design a device only with the analytical model, but the analytical model will drive the computational fluid dynamic models to understand the most dangerous configurations. Now let's move, let's stay on extreme waves, but in this case, it's more from an oceanographical point of view, so without structures, extreme waves by themselves. And they are, I'm pretty sure, you know, some of you have heard in the news, for example, this term rogue waves. So what do we mean by that? Well, there is not really a mathematical definition for that, but the definition that's, you know, mostly considered is that of very high, very tall waves that are high at least twice as high as the surrounding waves. And this is a very, very famous example. I'm sure Francesco knows this much better than me, but it's the example of the Dropner wave that was recorded on the 1st January 1995, So Dortmund is a platform, is an oil platform that was just outside the coast of, offshore the coast of Norway, so again in Northern Europe. And they had this sensor and buoy, and this recorded this wave. And this is really important because it's one of the very, very first examples where these extreme rock waves were measured. There were so many tales from fishermen before, which I mean were true. Definitely, I mean many boats were destroyed by these waves, but no one was able to record these waves. And this is one of the very first recordings. As you can see, this is again time, and we have surface elevation. The other waves are relatively, well, okay. I mean, they are still big because it's 4 meters. So the total wave height from crest to trough is about 8 meters, say about, you know, a 2-story building, which is still pretty big. But then we have this really big monster here, which is, so if you measure this wave from crest to trough, is about 26 meters, which more or less, just to give you an idea, is half the height of the Statue of Liberty. So it's really large. It's a really large wave. And they were able to recreate it in a lab only very recently, 3 years ago. And this is in this really interesting paper by McAllister and others. So this is a joint effort between the University of Manchester here in the UK, Oxford, and they were able to recreate this wave. And this is how it should have been, it should have appeared at the time. So as you can see, around the wave, there is pretty much nothing. So there are relatively small waves here. And then there is this, almost this beast, you know, this really, really tall wave. And of course, this is really dangerous because, like I said, there are, even nowadays, I mean, there are dozens of cargo ships that are hit by these waves every year all around the planet, and they are sunk. So and these cargo ships are filled with goods that are transported all around the world. So this is a huge loss in terms of course, economic loss and sometimes even human lives. So it's important for us to understand how these waves form. Now, one mechanism that has been identified is that these waves generate, well, Francesca's written several papers on this, so I definitely invite you to check them. But one mechanism that particularly intrigues me is that these waves generate when they meet some rapid changes on the seabed. And so far, most of the researchers have concentrated their analysis on 2-dimensional changes, but I wanted to study what happens in 3 dimensions. So this is some new analysis on what happens in 3 dimensions. And I'm particularly interested in submerged sails. You can see here a small sketch of what a sail looks like. This is actually not natural. This is man-made. I mean, there are several sails, as I learned, along the Mississippi River, which are probably to moderate the current. Of course, the type of sails I study are in the ocean. These are man-made. The ones I study are just natural sails or underwater ridges and canyons, for example. So all the places in the world oceans where there is a very strong change in the depth, like in this case, for example. And of course, we start with a mathematical model, so we have to idealize it, and we take a cylinder. So this is this area in dark gray is the seabed, and again, for idealization and to be able to solve it mathematically, we consider that this is flat. Later on, we show you other cases where this is not flat, but let's start with a flat ocean, and then we have our sail, and these 2 parameters are very important. So H1 is the full depth of the ocean, and H2 is the water depth above the sail. And this parameter delta is crucial. So it's the ratio between the 2 depths, the one above the sail divided by the one, the height of the total, the full ocean. Let's see what happens here. Again, we have some maths, and not surprisingly, we still have a Laplace equation. Waves, it's how we solve waves, how we study waves normally. By the way, this model is called potential flow model. And normally we solve a Laplace equation for this. And then again, boundary conditions on the surface, on the seabed, and on the sail's lateral wall. We solve this with several different methods. if you are interested, I've published, well, not just me, but our group, my group, and myself with my lab and my collaborators have published several papers on this. So I'd be, very happy to give you the references. But again, I want to show you the results. So once we solve this system of partial differential equations, we can then find what happens. So here are 4 different cases where the seal, in all these cases, the period changes, but the geometry is the same. So the seal is pretty much like this configuration. So our parameter delta here is 0.5. It means that the submergence, this delta is also called submergency 50%. So the total water depth is twice as high as the depth on the seal. So the seal is pretty much submerged. And when the seal is deeply submerged, like in this case, what we see is wave focusing. So what we are representing here, this is the geometry. This is the shape of the seal. So it's the contour of the seal, which is submerged. And these are the waves. So I've taken here the amplification factor. So when, which is always positive. So when the amplification factor is 1, it means there is no amplification. So effectively, the seal is not sort of working in the sense that there is no difference between normal waves without the seal and the waves that we have with the seal. But when the amplification factor is greater than 1, it means that the seal is amplifying the waves. And as you can see here, when we have this deep seal, what we have is focusing. So around the seal is pretty much all close to 1, so nothing really happens. But on the lee side of the seal, you can see that we are around 2. So the amplification factor is about 2. It means there is an amplification, and this is a focusing effect, very similar to the focusing effect I showed you before, but on a completely different scenario, where essentially the waves move around in the air around the seal, and then they focus at the back of it. And as you can see here, you can clearly see this focusing. What happens is that when we increase the period, so the waves become longer, this focusing area moves closer and closer to the seal. And so this is what we call the focusing regime. But even more interesting is what happens when we have a shallow seal. So now when our submergence is 25%, so that means that the water depth on top of the seal is only 25% of the water, the total water depth. So it means essentially the seal is very close to the surface. Then you can see that something completely different happens. So this is again the same plots for same periods, but with this new geometry. And you can see that there is dramatic amplification on the seal. And there is a really interesting wave pattern here that starts to emerge. And these are called, this is called the phenomenon of trapping. So as the seal height increases, for example, we're considering now a taller seal, its ability to trap energy increases. So effectively, this is trapping energy on top of it, and this energy is trapped. And so we have essentially the 2 phenomena that coexist. Focusing, as you can see, again, here the wave is pretty much focused in this area, but also trapping. And when these 2 phenomena coexist, we have very, very tall waves. This is 6 meters. The incident wave, so the incoming wave is 1 meter. So here the amplification factor is 6. This is definitely what would be called an extreme of rock wave. Okay, it's a very tall wave. And the waves around it are not really tall. So it fits into the definition of a rock wave. And here we can see this is a sort of summary of what happens. So this is again the period, and this is the amplification factor. When the submergence is high, so the seal is very much submerged, there is not much amplification. As we increase the submergence to 0.5, there is more amplification. And when we increase it even further to 0.25, so we decrease the submergence to 0.25, then we start to have very strong amplifications up to 6 times the amplitude of the incident wave. And this can explain why, for example, when we have strong variations in depth, also in 3 dimensions, we can get the generation of extreme waves. Finally, I want to show you something more computational. So all these models were mostly analytical. We did calculations by hand where possible, and only as a last resort, we use computers. Now I want to show you computer models. So what is called computational fluid dynamics, and this is really used when we have a more complicated geometry which is impossible to solve by hand or by simple computations or by solving the equations analytically, and we need to use these computational fluid dynamics models. And I've been developing a particular type of models which is called MPS, or moving particle semi-implicit method, which is a Lagrangian computational fluid dynamics method. By Lagrangian, we mean that we discretize the fluid into particles, imagine clusters of water essentially, and we solve for these particles. And it's really interesting method which allows us to do many things, because this can model, because of this Lagrangian approach, it can model all type of nonlinearities. So we can model really extreme waves in these cases, also interacting with structures, as I will show you later. So what we did is we started with the original formulation. As I reported here, we are not the inventors of this model. It was developed in the late 1990s by the group of Professor Koshizuka in Japan, mostly for chemical engineering. What we did is we modeled it and we changed it in a way that we are able now to apply to waves. Now we'll jump this and show you something more interesting. So we can apply to coastal structures. This is a seawall, and this is a numerical wave tank. So we have a piston here that's generating waves. The waves impact on this seawall, and we can use it to design. So for engineering purposes, we can use it to design the breakwater, to understand the pressure on the breakwater, the waves, and so on. This is the same exact model that is in action, actually. It's being built on the coast of Belgium, so not really far from here, just in front of where I am. In front of the UK, we have the Netherlands and Belgium. And they also did a model, a laboratory model that we use for validation. So this is a picture of the laboratory model. And this is what happens. So this is now the computational model in action. You can see that waves are coming. These colors represent pressure. Now, there is a nonlinear wave. This is a nonlinear wave incoming. You can see wave-wave interaction. And now there is, as you can see here, big, very strong actions on the berm and also on the seawall. Now, this is not a single drop. It's just use MATLAB for these models. And of course, these computational particles are points. So what I did, I increased the radius of these particles. Otherwise, you wouldn't be able to see this. But what we can do, in fact, as you can see here, we can model very violent interactions, and we can model splashes, wave-wave interaction here, wave breaking here. You can see some breaking. So this is very advanced modeling of nonlinear waves. And just to conclude my presentation, of course, we compared our results with the experiments. So the blue line, again, these are time series at two different points along the wave tank. And as you can see, the dynamics is definitely highly nonlinear. So we don't have, any longer this very nice sinusoid. The more the wave deviates from a sinusoid, the more nonlinear it is, more or less. I mean, you can understand it in this way. And the circles here are the experiments. And as you can see, there is very, very good agreement, despite, this phenomenon being highly nonlinear. There is really good agreement between the experiments and our MPS. And also, we compared our results with a different code, which is called SPH, which is also a particle method, but is more ancient in some sense. And as you can see, our method works better, particularly close to the top of the wave, and SPH is not working as well as our model. But in addition to this, our model is much faster. So it works better, it gives better predictions, but it's also much faster. In fact, for SPH, they used 150,000 particles, and it took them 80 hours for running an entire simulation. For MPS, even with a better resolution in terms of results. So we got better results with half the particles, and it took us only 15 hours to model a full, the full system for, I think, up to 12 seconds of, this wave maker generating the waves. And this is work in progress that I'm doing with several colleagues and collaborators also at the University of Plymouth. So now we are developing this model where we generate waves by moving this, almost, you can think to it as a landslide, moving this object on the seabed and see what kind of waves we generate in the highly nonlinear and dispersive regime. There are, of course, lots of works in terms of nonlinear, non-dispersive, but we believe this is one of the first works in terms of dispersive regime. And this can be applied to several applications, of course, landslide, generated tsunamis, but also there are some really interesting systems that they use in some places of the world, even here in the UK, to generate waves for surfers. And this is a system that I can put on the bottom of the ocean to generate waves for surfers. So in that case, we need to engineer to design it in a way that we get the waves we want. Just before concluding, acknowledgements, of course, I did this not alone, but together with many people, particularly people in my lab, Dr. Simone Michele, who is now lecturing in Plymouth, Dr. Filippo Gabriani, who was my former PhD student, Stephen Miller, who is my current PhD student, many collaborators. I mentioned Professor Frederick Diaz, Professor San Marco, lately Professor Borthwick in Plymouth, and Ken Doherty and Alan Harry from Aquamarine Power Limited. So I worked with this company, who is, they are a wave energy company, so they've also given us lots of suggestions and experimental data to test our models. And that's it. Thank you very much for your attention. And if you have any questions, please just ask.